Okay, good morning, everybody. Today we're going to be looking at graphing a quadratic equation. Chapter 4, Topic 1. Um, Now, in the previous chapter, in the previous topics, we've been graphing linear equations. Okay, linear equations form a straight line. Linear equations are also in the form of mx plus b, okay, slope-intercept form. Y equals mx plus b, this would be linear. You have an x and you have a constant. Okay, now this becomes a quadratic when you add an x squared to it. Okay, so if we put another term in front, an x squared term, well, now this is a quadratic. Okay, now it has an additional degree. Okay, it's 1 degree higher, which means the exponent is 1 degree higher. And this is now a quadratic. Okay, so a quadratic will typically have 3 terms. It'll have an x squared term, it'll have an x term, and it will have a constant, very similar to linear, but it includes an additional x squared term. Okay, now the standard form of a quadratic equation doesn't have mx or b in it. Okay, we use different letters. Standard form of a quadratic equation is ax squared plus bx plus c. Okay, that's the x squared term. That's the linear term, and this is the constant, and this means a is not equal to 0, because if it were a equals to 0, it would just be a line. Okay, but this x squared term makes it not a line. It actually makes it a parabola when you graph it. The graph of a quadratic is a U-shaped curve called a parabola, and it looks like this. Okay, it looks similar to the absolute value graph that we saw before. It is also symmetrical across the axis of symmetry, just like the absolute value, and it also has a low point or high point called the vertex, like an absolute value. Okay, but unlike an absolute value, which is pointed, this is curved. Okay, so this is curved, and we'll see how it makes that. Now, there's a lot of things you can find, a lot of information you can find from the equation of a quadratic. The equation can tell you a lot of things about it. The equation can tell you if the parabola opens up, like this, or opens down, upside down, like this. If the a value is positive, greater than 0, it opens up, and if the a value is negative, it opens down. And when I say a value, I mean the value in front of the x squared term. Okay, that's the a value in standard form, and that's the value in front of the x squared term. That just tells you how it opens. Now the vertex can be found by using this formula right here. And this formula gives you the x-coordinate of the vertex. Okay, it tells you where the x-coordinate of the vertex is. And you can find that by taking the b, making it negative, and dividing by 2 times a. That will give you the x-coordinate of the vertex. And then you can find the y-coordinate simply by substituting the x-coordinate into the equation here. Okay, plugging in the x-coordinate will give you the y-coordinate. The axis of symmetry is a vertical line that goes through the vertex, so it's the same as the x-coordinate of the vertex because it's vertical and it goes through the vertex. Now, when we're looking at standard form, ax squared plus bx plus c, the y-intercept is when x is 0. If x is 0, then these terms disappear and you get c. So you can quickly identify the y-intercept just by looking at the c value. Now, if the graph opens up like this, then the vertex represents a minimum. And if the graph opens down like this, then the vertex represents a maximum. And we typically refer to the maximum and minimum just by the y-coordinate. Okay, so the y-coordinate of the vertex is either the maximum or minimum value. We can graph the entire quadratic function or quadratic equation by creating a table of values around the vertex. This is very similar to the way we graphed an absolute value function. Okay, we put the vertex in the middle, So the vertex went in the middle, and then we picked two values above and two values below, or two values to the left and two values to the right, and we graphed those. And we did that just by plugging in each x coordinate. Just like the absolute value functions, these two have the same y coordinate, and these two have the same y coordinate because of the fact that it's symmetrical. So let's take a look at graphing a quadratic. Okay, so the first one we want to graph is y equals x squared minus 4x. So remember, we're looking at standard form here, ax squared plus bx plus c. So I'm going to start by identifying a, b, and c. A is the number in front of the x squared, which is 1. B is the number in front of the x, which is negative 4. And c is the constant, which isn't here, so it's 0. Now, since a is positive, we know that this will be opening up like this, okay, because the positive a value. If it were negative, it flips it upside down. Now, the vertex can be found, first we start with the x-coordinate of the vertex. The x-coordinate of the vertex can be found using this formula, negative b over 2a. Okay, so in this case, negative b over 2a, b is negative 4, so negative b would be 4. And 2 times a, 2 times 1 is 2, so the x-coordinate of the vertex is 2. So that's going to go in the middle here. To find the y-coordinate, we simply substitute x into the equation. So y is equal to x squared minus 4 times x. So x squared minus 4 times x, so 4 minus 8. Which is negative 4. So the y-coordinate is negative 4. We got 2, negative 4 as the vertex. Okay, so that means since this opens up and the vertex would be at the bottom, the minimum is what we have. We have a minimum. The vertex represents a minimum, and the minimum is at negative 4. The axis of symmetry is a vertical line that goes through the vertex, okay? It describes how the graph is symmetrical. It's symmetrical across the axis of symmetry. So the axis of symmetry is just the same as the vertex, okay? So the axis of symmetry would just be x equals 2, and that represents a vertical line that goes through 2 on the x-axis. The y-intercept, of course, would be the c value, okay? Because if you replace x with 0, all that's left is the c value. Well, the c value is 0, so the y-intercept is 0, 0. Now, we'll come back to the domain and range after we do the graph. Let's go ahead and fill out our table using x values that are to the left and to the right of 2. So to the left of 2 is 0, or 1. To the left of that is 0. To the right of 2 is 3, and to the right of that is 4. Okay, so keep in mind, these y-coordinates will be the same, and these will be the same because this is symmetrical. So first I'm going to plug in 0. Well, I already know what happens when I plug in 0. 0, 0, I get 0. So this one's 0, 0, and this one has a y-coordinate of 0 as well. Next, let me plug in 1. So I'm going to plug 1 into the equation. So 1 squared minus 4 times 1. So 1 minus 4, which is negative 3. Okay, so this is 1, negative 3, and this is 3, negative 3. And you can double check 3. 9 minus 12 is negative 3. Okay, so I want to graph these points here. 0, 0, 1, negative 3. So let me graph these here. So 0, so first let's do the axis of symmetry. The axis of symmetry is going through 2 on the x-axis, and the vertex is going to be on the axis of symmetry. The ordered pair for the vertex is 2, negative 4, so that's right here. I have 0, 0, the y-intercept. I have 1, negative 3, which is right here. I have 3, negative 3, and 4, 0. So 3, negative 3 is right here, and 4, 0 is right here. So now I can see my parabola. My parabola looks like this. And you can see it is symmetrical across the axis of symmetry. Okay, so that's what that dotted line there is for, is to show me that it's symmetrical across the axis of symmetry. Okay, so looking at my domain and range, my domain, of course, is going to be all real numbers. Okay, it's all real numbers because my graph extends infinitely left and right. Now the range is going to be the y-coordinates up and down. Well, since this has a minimum, the smallest is going to be at the minimum, which was negative 4, I think. Yeah, negative 4. And then it goes up from there, so it goes up to infinity. Whoops. Let's write this as an inequality. So the y-coordinates are everything larger than or equal to negative 4, which is the minimum. So it's everything above the minimum, which is the vertex. All right, number 2, y is equal to negative x squared plus 6x minus 8. All right, so identify the a, b, and c. A equals negative 1, b equals 6, c equals negative 8. This opens down like this because of the negative a value. The vertex, we first find the vertex by doing the x-coordinate, negative b over 2a. So negative 6 over negative 2, which is 3. So the x-coordinate of the vertex would be 3. I'm going to go ahead and put that in my table. The y-coordinate, I plug in 3 to find the y-coordinate. So y is equal to negative 3 to the second power plus 6 times 3 minus 8. So that's negative 3 squared is 9. 6 times 3 is 18. And minus 8. Okay, so negative 9 plus 18 minus 8. Negative 9 plus 18 minus 8 is 1. So the y-coordinate is 1. So 3 comma 1 is our vertex. Now, since this opens down and the vertex would be at the top, this represents a maximum. So the maximum is 1 for the y-coordinate, y equals 1. The axis of symmetry is the x-coordinate because it's a vertical line going through the vertex, and the vertical line going through the vertex would have an equation of x equals 3. The y-intercept is always the c value because if you plug in 0 for these, they disappear, so you're just left with this. So 0 plugged in for the y-intercept gives you negative 8. If I fill out my table, to the left of 3 is 2 and then 1, and then 4 and then 5. These two are symmetrical and these two are symmetrical. So I'm going to figure out what the rest of this table is. So let me plug in 1. So y equals negative 1 squared plus 6 times 1 minus 8. So negative 1 plus 6 minus 8. So negative 1 plus 6 minus 8 is negative 3. So this one's negative 3 and this one's negative 3. Next, I'm going to plug in 2. So y equals negative 2 squared plus 6 times 2 minus 8. So that's 2 squared is 4, so negative 4 plus 12 minus 8. And that's looking like it's probably 0. Correct, that is 0. So 2, 0, and 4, 0. So that's my table here. Now I can go ahead and answer my domain and range because my domain is all real numbers because it extends infinitely left and right. My range is everything below, because we have a maximum at 1, so it's everything below the maximum. So y is everything less than or equal to the maximum, which is 1. So everything below the maximum. And now I can graph this. So I'll graph my axis of symmetry, which is at 3. And it looks like I'm going to have to erase some stuff. Let me take this somewhere else so I can use it. Okay, so my axis of symmetry is at 3. My vertex should be on the axis of symmetry. It's at 3, 1, which is right here. And then we have the points 2, 0, and 1, negative 3. And then on the other side, we have 4, 0, and 5, negative 3. And we can see our graph here. And it should be a parabola. So make sure you don't make it a point, okay, because it should be a curve. So it curves up here, and it looks like this. All right, let's look at our last example here. Number 3. We got y is equal to 2x squared plus 8x plus 7. This a is 2, b is 8, and c is 7. Okay, so this opens up because the a value is positive, so it's going to look like this, vertex at the bottom, which means it has a minimum because the vertex is at the bottom. To find the actual vertex, we need to find first the x-coordinate of the vertex, negative b over 2a. So negative 8 over 2 times 2, or negative 8 over 4. So the x-coordinate is negative 2. I'll put that in my table as well. To find the y-coordinate, I need to plug negative 2 into the equation. So y is equal to 2 times negative 2 squared plus 8 times negative 2 plus 7. Okay, so always do exponents before multiplication. So that's 2 times 4, because negative 2 squared is 4. So 2 times 4, 8 times negative 2 is negative 16, and plus 7. So I'm looking at 8 minus 16 plus 7, which is negative 1. So the y-coordinate of the vertex is negative 1. So the minimum is the y-coordinate, so that's negative 1. The axis of symmetry is the x-coordinate, so x equals negative 2. And that's a vertical line going through the x-axis at negative 2. The y-intercept would be plugging in 0 for x. This term would go away, and this term would go away, so we'd only have y equals 7. So 0, 7 is the y-intercept. The domain is all real numbers because it extends infinitely left and right. The range would be everything above the minimum. The minimum's at negative 1, so it's everything above negative 1 for the y-coordinates. Now for the table, to the left of negative 2 is negative 3, to the left of that is negative 4, to the right of negative 2 is negative 1, and to the right of that is 0. So I'm going to go ahead and plug in, because remember, these two are the same because of the symmetry, and these two are the same because of the symmetry. So I'm going to go ahead and plug in negative 4. So y is equal to 2 times negative 4 squared plus 8 times negative 4 plus 7. So 2 times 16 minus 32 plus 7. So that's 32 minus 32 plus 7. So that's just 7. Okay, so that's 7, that's 7. Okay, next let me plug in negative 3 or negative 1. It actually doesn't matter. So y is equal to 2 times negative 3 squared plus 8 times negative 3 plus 7. That's 2 times 9. 8 times negative 3 is negative 24 plus 7. That's 18 minus 24 plus 7. So 18 minus 24 plus 7 is 1. So this is 1 and this is 1, positive 1. Okay, so I'm going to use this to set up my graph. Move it over here so I can actually use it. Now, my vertex is going to be at negative 2, negative 1. Now, to help us graph it, we want the axis of symmetry going through the vertex because the left and right side of that line should be the same. Okay, so I have negative 4, 7, negative 3, 1, negative 1, 1, and 0, 7. Go ahead and connect these to make my parabola. And there we go. As you can tell, it's a little bit thinner than the previous ones. Now, there's one that's not on here that I do want to add on here, which is the parent function, the quadratic parent function. Okay, so we talked about parent functions when we did transformations. Okay, we always transformed, when we did absolute value, we transformed the parent function. The parent function is the graph with no transformations applied to it. Okay, in the case of quadratics, the parent function is just y equals x squared. Okay, that would be no transformations applied to it. It's just the basic quadratic. It doesn't have anything else. Okay, so I do want to look at what the parent function, the most basic non-transform quadratic function, looks like. It opens up because a is 1, b is 0, c is 0, so it opens up. Looks like this. The vertex, the x-coordinate, is at negative b over 2a. Well, the b is 0, so 0 over 2, so the vertex is 0, and if you plug in 0, you get 0. So the vertex is at 0, 0. Without any transformations applied, the most basic quadratic is at 0, 0. And of course, it represents a minimum at y equals 0, at the bottom where the vertex is, and the axis of symmetry is also at 0. The y-intercept is the c value, which is also at 0. So the vertex and the y-intercept are the same thing. It's the origin. And if we fill out the table, remember these two are the same, and so are these two. So first we would plug in negative 2, so negative 2 squared, which is 4. So this is 4 and this is 4. And plug in negative 1, so negative 1 squared, which is 1. So this is 1 and this is 1. Okay, now the domain of this is all real numbers. And the range would be, since it's opening up and the vertex is at the bottom, a minimum, then it would be everything greater than or equal to 0. Now let's see what this graph of this parent function y equals x squared looks like. So this is without any transformations applied to it. Y equals x squared. So we had the vertex at 0, 0, and the axis of symmetry is going through that point, so like this. We had 1, 1, and 2, 4. We had negative 1, 1, and negative 2, 4. So this is the most basic absolute value, this is the most basic quadratic function without any transformations applied to it, the graph y equals x squared. Okay, I really should have done this one first because it's the most basic one. I just didn't think about it when I started the video, but I'll probably do it first in class. Okay, so go back and compare the ones that we graphed before and see if you can you can tell what transformations have been applied to them, okay? Because every one that we graphed today has been some shape like this, but the vertex has been transformed, the graph has been transformed. See if you can figure out what transformations have taken place in the examples that we saw earlier.